All right, so thank you all for joining for this new reading group session organized by Continual AI. Today we have the pleasure to host Shuang Li from MIT, and she has been working on these very interesting and original paper, energy-based models for continual learning. So we hope to hear from her about these very interesting developments that can, I hope, spark new interest in this area of research, specifically about energy-based models, and maybe offer us some suggestions that we can use in our own research. So I was really pleased, as I would say before, to see this new work out. And please, Shuang Li, go ahead now. The stage is yours.
Sure. Yeah. Thank you for inviting me. I'm Shuang Li. I'm a first-year PhD student at MIT. And today I'm going to present my work, energy-based model for continual learning. This is a joint work with Elon, Guido, Antonio, and Igor. So in today's talk, I'm going to do 4 things. So I will first give a brief introduction of what is continual learning. And secondly, I will talk about how is continual learning related to AI reinforcement learning, lifelong learning, transfer learning, and so on. And thirdly, I will talk about why we use energy-based model to solve the continual learning tasks. And finally, how well can energy-based model perform on different continual learning settings? So what is continual learning? So as human, we interact with the world, and we get feedback from the environment and other people, and we consistently improve ourselves. So as shown in this video, so the baby first learn crawl on the ground, and after they get older, around 1 year old, they learn how to walk. And after that, they learn more sophisticated skills, such as open the door. And the human can not only learn these new skills, they can also transfer what they learned from the past to solve the new task and adapt themselves to new environment faster. And here are several examples to show how it works. So in the first example, so I'll show you a sequence of A1, B1, C1, A2, B2. And I think it's not hard to know what will come next. It's C2, it's not hard. And in the second example, I'll show you a picture. And I think someone may know the name of this animal, but some people don't. And now I tell you, this is purple slug. So do you know what's the name of this animal? And I think it's also not hard. You can say it's yellow sea slug. So why we are so good, like infer something that we never seen before? Why can we, predict something like what will happen next? I think one reason is that we are really good at finding regularities and use these regularities to predict the future. And in real world, these regularities occur repeatedly and are dependable enough for us to use them and quickly adapt to new environment. And that's why we want to start a continual learning problem. So we hope to understand the past better so that we are able to predict the future better. And this slide is copied from Mark Ring. And as we can see, the continual learning is a core problem in AI, and it has intersections with many other research problems. And the continual learning is a problem that every learning method that may face in the future. But now people focus on some simple problems. For example, the continual learning on classification. I will briefly introduce this problem setup and the evaluation matrix. So let me take the MNIST as an example. So there are 10 classes in total, and we divided the dataset into 5 subtasks. So in each subtask, we have 2 classes. For example, in task 1, we have class 0 and 1, and in task 2, we have class 2 and 3. And there are 2 commonly used evaluation metrics. The first one is task incremental learning, and the second one is class incremental learning. So in the task incremental learning, given an image, we need to predict this image is from the first class or the second class. And in the class incremental learning, we need to know what the digit it is, and we need to predict the label from all thin classes. So the class incremental learning is a harder problem. The biggest challenge in continual learning is the catastrophic forgetting problem. So as shown here, we have 5 different tasks, and the accuracy of the first task after retraining on the first task is very high. It's close to 1, but after we train on the second task, it suddenly dropped to 0.5. And this means the model forget the first task. And similarly, the model has high accuracy on the second task, but it's become very low when it's trained on the third task. This is because the data is not stationary, and the new memory overrides by the old ones. So there are existing work try to solve this problem from 3 different ways. The first one is regularization-based method. The second one is memory-based, and third one is structures. So they can improve the accuracy, but they also have some limitations. For example, in the regularization-based method, so people usually use a regularization loss to penalize the change of parameters that are important to previous task. However, this will gradually reduce the model's capacity to learn new tasks. And we find that they usually perform very bad on the class incremental learning setting. For the memory-based method, some people use extra memory to store some previous data, and some other people use extra model, for example, to train a generative model to generate some data and train it with the new task. The last one is structure-based model. I think people usually add new architectural blocks when they train new tasks. So in our paper, we do not using any extra loss or extra memory, extra model, but we can still perform well on the class incremental learning setting. So this is the architecture that existing works use. They are mainly based on the softmax-based classifier. So as shown in the left part, given an input image, we feed it into a neural network. And after a softmax, we output a vector to represent the probability on different classes. And in the red part, it shows the classes appears during training when we trained on each task. So people use this softmax layer and to compute this conditional probability. And in this part, it's the summation over all thin classes. However, this will cause a problem. So for example, when we trained on task 2, we only see classes of 2 and 3. And in that case, we will increase the probability of 2 and 3, and we will decrease the probability of 0 and 1. And during the test time, the model is more likely to predict the 2 and 3. And in that case, the model forgets the first task. And this is an example to show this. So in the first row, we show the negative probability of each task data on different classes. And this is the performance on the permutated MNIST dataset. So in this dataset, we have 10 tasks, and each task has 10 classes. For example, in task 1, we have class 0 to 10, and in task 2, we have class 10 to 20. So the ground truth prediction should along the diagonal. The diagonal should be dark because this is the negative probability. But as is shown here, this is the softmax-based classifier after training on task 9. We can see the lowest negative probability appears between 80 to 90 for all the tasks. This means this model is more likely to predict labels from the current task and forget previous tasks. And similarly, after it trained on task 10, the lowest negative probability shifted to 90 to 100. And in the second example, this is the predicted class distribution after training on each task. So we have 5 different tasks. And for example, after we train on task 2, the correct prediction should be uniform distributed over 1, 2, 3, and 4. But now the softmax-based classifier only predicts class 3 and 4. So in our energy-based model, we try to estimate the probability, the joint probability of x and y using this function. And E is the energy function which maps the input x and y to a scalar value. And Z is the prediction function is used as normalization. And in practice, we find that even using this conditional probability, we can achieve good results. So given an input image x and a label y, if they are matching, we will treat as a positive pair. Otherwise, it's a negative pair. And we want to minimize the energy of positive pair and maximize the energy of negative pair, so that we use this training objective to achieve this goal. This is the energy of the positive pair, and these are the energies of negative pairs. And during the prediction, we fit in an image x and all possible labels, and we use the label that has the minimum energy as our prediction. So these are the model architecture of the softmax-based classifier and our energy-based model. So our energy-based model takes x, y, and input and makes their information in the middle and output their energy. And now, let's see why energy-based model can mitigate the catastrophic forgetting problem. So as we can see that in our training objective, we have a part represent the positive pair, and this is a part to represent the negative pairs. So in this case, how do we select the negative samples is very important. And here we design 3 different ways to select the negative samples. So in the first one, we select the negative samples using all the same classes, like this one. And the second way, we select the negative samples using all the classes appeared in the current batch, as in this one. And the third sampling strategy is that we only select one single negative from the current batch. And we can see that it achieved the best result. And this means if we only select one single negative example from the current batch, it causes the minimum suppression of the classes from previous task. And that's why it has better performance. And another reason why energy-based model is better is this because of the label conditioning architecture in energy-based models. So we also do an experiment to test this. This is the original softmax-based classifier. And these labels in the dash box are the classes used during training. But now, instead of using all the same classes, we only do the normalization over classes in the current batch. And this is the result using their original training objective. And these are the results using our modified training objective. And we can see that there's a big improvement after we do this modification. But again, our energy-based model is still outperform the baselines, which shows that our label conditioning architecture is also useful to mitigate the catastrophic forgetting problem. So recall that our energy-based model takes an x and y as input and outputs the energy. So it's very flexible for us to add to dynamically add new classes. And also the design of the model architecture is very flexible. As long as the input is x, y, and the output is their energy, the model can be very flexible. So here we design several different architectures. For example, we combine the information from x and y in the beginning, in the middle, or in the end of the architecture. And we show that if we combine the information of x and y in the end, it has the best performance. So we also test a different normalization method to combine the information from x and y. For example, the L2 norm and softmax. And we find that using softmax achieves the best result. And this is a comparison of our energy-based model with baseline methods on the task-aware setting. I will explain later what this setting is. So these are the this is are the baseline method, and this is our energy model. And we can see our energy-based model has a big improvement on 4 different data sets. And this is energy lab of the softmax-based classifier and our energy-based model. So the correct prediction should along the diagonal. And the darker the diagonal is, the better the model is in preventing forgetting previous tasks. And this is the predicted class distribution. As we can see that our energy-based model can output all the classes instead of just the classes in the current task. And this means our energy-based model still remembers the past tasks. And this is the test accuracy curve along the training. And this is the softmax-based classifier. And we can see there suddenly drop after we train on new tasks. And the softmax-based classifier using our training objective is better. And our energy-based model is the best. So we have shown 3 reasons why energy-based model can mitigate the catastrophic forgetting problem. It's because of our training objective and the label conditioning architecture. And to use a proper network structure is also helpful. So next, I will show you 3 explanations of why energy-based model is better. The first one is model capacity. So in this, to test the model capacity, we do 2 different experiments. The first experiment is we test the model capacity on generated images. So we generate 32 by 32 images, and each pixel is uniformly sampled from -1 to 1. And each image is assigned a random class label between 0 and 10. And note, our energy-based model and the classifier has similar number of parameters. And here we test the model capacity of SBC, the soft-based classifier, and our energy-based model using 3 different model sizes. And the solid lines are our energy-based model, and the dashed line are the softmax-based classifier. And we can see, given the same number of training data points, our energy-based model has a higher accuracy, which means our energy-based model can memory more data, and our energy-based model has larger model capacity. The second experiment we did is on the natural images. So we use the images from CIFAR 10, and for each image is randomly assigned a class label between 0 and 10. And after training, the energy-based model top 1 is around 82, and for the classifier is 42. So our energy-based model is much better. So next, I'm going to show the parameter importance. So this is inspired by the work in overcoming catastrophic forgetting in neural networks. So in their paper, they use a Fisher matrix, an information matrix, and the diagonal elements of this matrix measures the importance of each parameter to a given task. So the density of the diagonal elements indicates the proportion of important parameters. And the more density it is, the more parameters are important for the given task. So less parameters can be used for new tasks. And ideally, we expect this value to be sparse. And this is one example to show this. The x-axis represents each different parameter, and the y-axis is the Fisher Inframatrix value. And we can see our energy-based model is sparser than the softmax-based classifier. So the last one is the interference with past data. I'll skip this part And I only show the conclusion that our energy-based model causes less interference with old data when updating parameters. And if you are interested in these 3 different analyses, you can find more details in our paper. So I think most existing work are based on the standard class incremental learning setting, and which we call it boundary aware. This is because there are fixed boundaries between different tasks, and the model is first trained on the first task and then move to the second task. And also the model must be informed when the tasks are switched during training. But in real world, we find that the task boundary is not available, and data is usually given in a streaming fashion. And this, we notice a new evaluation setting, which we call boundary agnostic setting, as shown in this figure. So the data from task 1 gradually decrease, and the data from task 2 will gradually increase and then decrease. And we can find there's a like a mixture of data from task 1 and task 2 in the middle. And we show that our energy-based model can solve both settings and can achieve good performance on them. But some existing work that relying on the task boundary to decide when to consolidate the knowledge cannot do the boundary agnostic setting. So this is a comparison of our energy-based model with some baseline models. And this, we can say that our energy-based model outperformed the baselines by a large margin on 4 different data sets. So to recap, we showed the energy-based model can naturally deal with the challenge problem in continual learning, including the boundary agnostic setting and the class incremental learning without using any replay. And secondly, we use a contrastive divergence training procedure, and we show that it provides a natural way to deal with the dynamically growing classes, and that it significantly reduces catastrophic forgetting. And thirdly, we propose to learn new conditional gains during the training process, which makes energy-based model parameter updates cause less interference with old data. And fourthly, we show that in practice, our energy-based model brings a significant improvement on 4 standard continual learning benchmarks. And finally, we provide different visualization results and analysis from different perspectives to explain why energy-based model causes less catastrophic forgetting. So energy-based model can not only do the classification problem, it can be applied to many different domains. For example, in this paper, we use energy-based model to solve the generation problem, and here we do the compositional visual generation. So I will briefly introduce this paper. So we learn independent energy functions of each separate concept. For example, concept color and concept shape and concept size. And then we treat the generation as optimization over energy function, and the composition as optimization over multiple energy functions. And we design 3 different operators, conjunction, disjunction, and negation, to combine different energy functions. And here are some examples generated using our energy-based model. So in the first row, the images are generated conditioned on the smiling concept. And in the second row, it's conditioned on the male concept. And then we combine the smiling and the male, and without retraining the model, we can generate some combined, some images that has both concepts, smiling and male. And this is examples smiling and not male. And here are more operators, smiling and female, or not smiling and male. So it comes to another question. So can we combine these concepts in an incremental manner? And we do an experiment to verify this. So in this experiment, we first learn a position concept with shapes of fixed size and color. And then we learn a size concept with fixed color. And then we learn a color concept with all variants. And this is the image generated conditioned on the precision concept. And this is generated by combined a new size energy-based model and combined with the previous learned precision energy-based model. And finally, we combine the precision, size, and color to generate some objects like in different positions with different size and different colors, and they are never seen during the training. So this is one of work we are doing right now. So we want to combine this compositionality and the continual learning, and we want to try this in the image generation task. And secondly, instead of just doing the continual learning in classification problem, we also want to extend our work to other domains, for example, image generation and the reinforcement learning. And this is the project webpage. And if you are interested in energy-based model, there's also a summary of our recent work on energy-based model. Thank you very much.
Thank you so much, Shuang, for this very interesting presentation. And I want to say that I really enjoyed several aspects of your talk. One very simple aspect of it was that you spend it seems like you spend quite a lot of time trying to come up with some interesting graphics, and ways to explore what's happening behind the scenes. So I really appreciate that within your paper as well. I mean, there are some ideas that are also very original in that sense. So I will definitely look more into them. And thank you for your work. But maybe I can start with a question before leaving also the other people here in the audience ask their question. I wanted to know because I didn't see it in your presentation. I'm not sure it's present in the paper, but I wanted to know something more about the efficiency and scalability of these kind of techniques using especially energy-based models. Because you have tested on different data sets like NIST and CIFAR. But I'm often try to focus on the idea of scalability for an algorithm. So I wanted to know if you had some more insights about the time that you needed to let these experiments complete, and the memory usage of your method, or just the scalability in terms of if these overheads are growing linearly or in a different way with respect to the number of tasks that you process. So these kind of aspects, have you considered them? Do you have some ideas about them?
Sure. Just to so you're talking about the computation time, right?
Yeah, like memory and computational overheads and how they scale with respect to the number of tasks that you process, as well as the complexity of the task itself, like for example, the dimensionality of the data and something like that.
I see. So I think that's a great question, and I should mention this in this talk. So in our energy-based model, during training, we control that we use the same number of iterations as the baseline models. So for the baseline model, we run ourselves, and our energy-based model, they use the same number of iterations to train on each task. But for our energy-based model, we find that if we train it longer, it usually has better performance because it takes a longer time for energy-based model to convert than the soft math-based classifier models. And secondly, we find that our energy-based model, in terms of the evaluation, it will take longer time because as shown in this architecture, we need to fit in an X and all possible Y during the evaluation time. And we select the Y that has the minimum energy as our prediction. So this will take a longer time than the other baseline models. In terms of memory, so we do not using any extra memories here. And we do not store any data. And here is the architecture. And actually, in our energy-based model, we use fewer parameters, especially on these 4 different data sets. We use less parameters than the baselines, but our performance can still outperform theirs. Yeah, did this solve your question?
Yeah, absolutely. Yes, thanks. Do we have any more questions for Shuang and their work?
Yes, I have a question. First of all, thank you, Shuang, for your very interesting talk. I really appreciated all your method and the papers. Not really a question, but just an explanation on if you can explain again how you select the negative example when you train your model.
Oh, sure. So yeah,
Thank you.
thank you. Yeah, in this slide, it shows how we select the negative samples. The first strategy we use is that these negative samples are consist of all the classes seen, but except the ground truth label. So we have a ground truth label of a given image, and for example, in this CFAR 100 dataset, we have 100 classes. So there are 99 negative classes for a given image. And we use all these 99 images as negative sample to train this objective function. And the second way is we only use negatives from the current batch. So for example, in the last task, the classes are from 90 to 99, and we only select negative samples in the current task, which means there are non-negative class and there's one positive class. And the final strategy is we select only one single negative from the current batch or current task. And this means there's only one negative sample here, and there is only one positive sample here for each input image X.
Yeah. Okay, thank you. It's more clear now. Thank you.
Okay, yeah, thank you.
Any more questions?
I have one question.
Please go ahead.
Okay. First of all, yeah, it is a really great paper, and yeah, like as what I understood, like there are two things. One is the objective energy-based objective function, and the other thing is the label selection method. So I was wondering, like, have you tried applying this label selection method for training in some traditional algorithms like LWF and like all these algorithms? Like, is it possible that we can see the improved performance of those traditional algorithm using this new label selection method?
Oh yeah, you mean this using our label selection method? This is one experiment we did here. So in the original traditional like baseline models, they do the normalization over all thin classes, right? But now we only do the normalization over classes in the current batch or current task. And this is the performance of using their original, normalization method, and this is using our new method. And we can see there's a big improvement here.
Okay. So like when you say softmax-based classifier, so like in that, like it includes like what training method it includes, like which algorithm for training you include?
I think all the baseline method I compare is based on this softmax-based classifier. So because they design different methods different ways, but the input is always an image X, and output is a vector to represent the probability on different classes. And all the baselines I show here are based on this softmax-based classifier.
Oh, okay, cool. That's good. Thanks.
And I think the most existing work on continual learning to solve the classification task is also based on the softness-based classifier, and that's why
Yes.
I like to explain this part.
Yeah.
Thank you.
Thank you.
Do we have any more questions for Shuang? I could see that there's also a co-author here, like Guido, that I mean, we had a few sessions back, meetup back, discussing about other topics, but I was surprised to see Guido as well involved in his work. So I think that he's cross-pollinating a lot. He's great field, continual learning, and I say hello to him.
Oh yeah, I think Guido helped a lot. So for me, this is my first paper doing on continual learning. And I think Guido is very experienced in this domain. And for some baseline and some evaluation matrix, he do give me lots of feedback. Yeah.
All right, so if we don't have any more questions, then I would say that I take this opportunity to say good holidays for those of you that can enjoy it within this pandemic, but good holidays, and have a nice Christmas, because we won't have for 2 weeks our weekly reading group, and we will start again the 8th of January 2021 with a presentation of the paper Generalization Guarantees for Continual Learning with Orthogonal Gradient Descent. So thank you all again for joining. Thank you so much, Shuang, for your great presentation. I hope to see you again, possibly on a conference, on a real conference next year. But in any case, have a nice weekend. See you.
Yeah, thank you very much for inviting me. Have a great day. Bye.
You too. A pleasure.